All right. Thank you for coming to my talk, A Slice of Modern Program Analysis. I often hear others describe reverse engineering and especially program analysis as the hard thing. There's a lot of things we can do before we get to reverse engineering, and a lot of you guys treat it as a last resort. And program analysis is hard. It involves a tremendous amount of math, and math can be scary. Now, don't walk out. This is only a slice of. There is a lot that This talk aims to build a bridge between developers, researchers, reverse engineers, to benefit from the concepts and consequences of program analysis and graph theory using a slick interface, a simple API, on an open source MIT license, pluggable framework, all built on top of Binary Ninja. So, if there's nothing else that you take away from this talk, it should be that graphs are one of math's and computer science's favorite babies that people have exploited to extraordinary benefit across fields, including program analysis, and graph theory should be your favorite baby too. With the right tools and the right abstractions, you don't need to completely understand the underlying theory to utilize or benefit from it. How many parents understand their children? This talk is my love letter to graph theory, and I hope that it inspires all of you to exploit our new favorite baby as well. I hope that you use GraphView more. I hope you create your own graphs and build on top of the framework I'm releasing today. So, graphs are really cool. One of the most fundamental benefits that you get from graphs immediately are the patterns you can recognize. You get while loops, do while loops, early returns, infinite loops, if-else chains, command dispatch, initialization, tons and tons of patterns just fall out of graphs when you start looking at them. In this particular case, we've got two loops that I can immediately recognize off the top. And often when I see a pattern like this, and this is by no means universally true, where an entry block goes right into a loop, followed by another loop, that first loop is going to be some sort of initialization. In this particular program, it's just taking input, and then that second loop is going to be processing that data. Again, these can both be processing loops, they can both be initialization, they could be a dozen things. But in a lot of the binaries I'm looking at, this is a pattern I often see. And then it's followed up by a final decision block at the end, which returns some results. So GraphView is great. The more you use it, the more patterns you'll be able to recognize, and the more structures you'll be able to find. So here are some of the most basic patterns you'll see in graphs. We've got an if-else chain here. You've got your three cases in the middle there, all merging into a block underneath. This is what a loop looks like, and you can see an early return as well as the normal exit from the bottom there with the break. Got do-while loops, just a loop from the bottom going back up to the top. You can return from the bottom there, exit from the bottom there. And then command dispatches, one of my favorites. You've got a node with a bunch of other nodes coming out of it. So, when you zoom out, you can start to recognize these patterns together. Control flow sinks and subgraphs, isolated regions of nodes, more formally, dominance frontiers. But in this graph, I can recognize up in the top right there, we've got a early return from the function, goes down to the bottom. In the top left, we have a case that switches a bunch of that processing in the middle. Of course, then we have the processing in the middle. We've got two algorithms implemented in this function, one on the left, one on the right. And then we've got whatever that final decision logic is at the end. So I use this to inform my reverse engineering. Maybe start by checking the bounds applied to the arguments of the function. Check what that early return is. Check what skips all that processing. Don't look at all the complicated stuff in the middle. Maybe you go to the end and you start working from the return value and you figure out what you need to read to figure out what affects the return value. And then eventually you probably will need to reverse that algorithm in the middle, but you might not need to. You might be able to find a bug in that special case that skips the processing, for example. So, TLDR, GraphView is amazing. Taking chunks like we just did, breaking functions and programs down to their constituent components that we can reason over is what's called slicing. And we'd love to be able to describe more or show more in graphs. They help us reverse faster. They help us understand programs faster. Patterns fall right out. And they can provide us more robust interaction and annotation tools in our reverse engineering tools. But how? So I'm introducing Tonto 2.0 today. It is an arbitrarily pluggable, context-aware flow graph viewer for anything. I can show you guys here the plugin manager if my water bottle doesn't slide off the desk. Cool. So it's released. You guys can go download it. It's open source. You can go check out the repo if you'd like. And my slides are up there too. So users are going to be able to understand code faster, as I promised you. It's more immersive. You're going to stay oriented in the binary. You're not going to get lost where you are. You're going to be able to take better notes. For developers, you get a nice hierarchical organization system that allow you to write and debug your plugins, create new simplifications, and help the tool users. And then I'm hoping researchers will be able to develop new algorithms, create powerful visualizations, and discover new insights into programs. So I've been thinking about these problems for a long time. I've been exposed to a lot of very hard problems where you get multiple versions of a graph of the same program or graph that are slightly different, and you'd like to be able to reason over them all simultaneously. And I'm always also thinking about the next plugin I can make for Binary Ninja. I love making visualizations, and our tools are interactive. Interaction was novel in 1991 when IDA came out, and it took them 15 years to get GraphView into the product. And it's been 20 years since then, so where are new visualizations? I started graphing the problems I saw, and people seemed to like those graphs enough that I released Tonto 1.0. Of course, I'm not the first person to discover that graphs are cool and can be very useful. People have known this for a long time. Ghidra implements a handful of slice types. In particular, they've got backward slices where you select a variable and it highlights all variables that affect the value of the variable you've selected. And they also have forward slices where you select a variable and it highlights all other variables that it affects the values of. IDA has built-in node groupings to allow you to select a group of nodes and collapse them into a single one. Mandiant built a plugin called Simplify Graph, which adds a lot of useful automations for you around that. This one in particular is the create switch case subgraph. So you can see we take a really nasty control flow graph on the left, and then on the right we can make a nice simplified version of it where you get to see the 5 cases there and then maybe a default case and some return logic. So those are 2 examples of slices. Ghidra implements what I'm calling variable slices, variable-based slices. The simplified graph slices are going to be simplification-based, reducing the number of nodes you need to analyze. You can also make informative, interactive you can slice over the call graph. You can slice over the control flow of individual functions. You can make data flow slices, and you can do inter-procedural analysis, slicing, data flow. Really, whatever you can imagine, your imagination is the limit. So let's start with the problem and see how slicing can help with that. One of the first problems people have is just getting started analyzing a binary. You need to find interesting locations that you want to read that might produce bugs or whatever it is you're trying to understand. There's tons of current solutions for this. You can trace the program and only analyze near where the program executed so you don't get lost in the weeds. Particularly if you know the region of code that you're interested in got executed during that trace, then you can just focus on that. You can start from strings, find interesting strings in the binary, and go to the cross-references for those, see what functions are using those strings, where they're being used, go from there. You could identify external function calls in the program and start doing data flow slicing. External function calls serve as the interfaces for our program, where data comes in and where data goes out. So very interesting places to start, but it's always useful to have more tools, right? More ways to tackle a problem. So let's talk about one of my favorite underexploited properties of a program, call relationships, call graphs in particular. So this is a portion of Bomb Lab. For the uninitiated, Bomb Lab is a very well-known academic example that universities use to teach students how to reverse engineer. It's got like 6 phases and a secret phase. It's got a couple things. We'll get into it. And this is a portion of Bomb Lab. I'm sorry, it's a bit small. The nodes are functions, and the lines are arrows that represent a call from one function to another function. And by looking at this graph, I can recognize a couple patterns. Up in the top right there, we've got some subsystem. Doesn't seem to call into anything else. We'd have to click through it to figure out what it's called by, but it's isolated. We don't really need to care about it necessarily. And then in the bottom left here, we've got a whole bunch of functions that don't call other functions. These are going to be our external functions. This is going to call into libc or any other library, but we don't have the insight into what they then go and call. So they end up stacking up in a vertical column like this in our graphs. And then we can also recognize the actual main control flow logic in the program. We can recognize main, in effect. If this binary was stripped, if it was a bigger binary, we can recognize these sort of dispatch patterns, and that's where interesting stuff in our program's happening. That's where the main logic in our program is coming from. So if we zoom in on that region, we can see main right at the top. And main calls into the 6 phases of the bomb, plus the secret phase. And then down at the bottom, we can see explode. So maybe just analyze the paths that don't call into explode. And also congrats. Now you know how Bomb Lab works without having read a line of code, because you can just analyze the function, the call relationships, get these patterns out. So let's take a look at that. All right, I'm going to open, so this is Binary Ninja. Tonto is implemented as a view. So I'm going to go ahead and split our view in 2 here. You'll see right now we've got high-level IL on the left, and we've got disassembly on the right. Click around in those, and it sort of shows you all the lines of assembly that constitute that call to check answer. But I can go up here, I can open up Tonto, and from here we can make a slice. And we want that full program call graph slice. The name's optional. Now, if I go back to main, we can see the full call graph for the program now on the right. It's a little big, hard to see. So let's, again, just zoom back into main, navigate to where we want. And as I click around on the left, it's going to navigate you on the right. And as you click around on the right, it's going to navigate you on the left. So I think that this makes just a fantastic way to interact and explore a binary, in addition to discovering those isolated modules. I think I also wanted to show you guys, let's take a look at it in a bigger binary. Let me just cheat and check my notes here. No, I'm getting ahead of myself. All right. So this is what the code for the full call graph looks like. Not going to go over the code for all the slices today, but I just want to show you really, really simple to implement. You just import Tonto at the top. You have an init function, takes a binary view, or rather, doesn't take a binary view. It takes a Tonto view, which is a Qt object, which means you can do all sorts of UI hacking. It also, from it, you can get the binary view. And then you just need to implement this one function, getFlowGraph. GetFlowGraph creates and returns a flow graph. In this instance, I cycle through all the functions, I create them as nodes, I populate the lines of each node with the function signature, and then I connect them at the end. You register it with a name, and it's just that simple. So I'm hoping you all go home and you write these simple slices. You've got plenty of open source examples to build off of. You can copy and paste them all into ChatGPT and see how well it does. Describe the problem you want to solve. But full call graph is great for discovery. You can recognize those different modules within a program that are tightly connected, and you can recognize calls into other regions of the binary. So functions, if you recognize a group of functions that only call each other, those are going to likely be like the private members of a class. But when you start to see functions that are called from elsewhere in the binary, those are going to be your public interfaces for the class. But in the full function call graph, those are going to be in very different areas of the view. So it makes it hard, the full call graph makes it hard to analyze those interesting interfaces that we want to be able to look at. So the full function call graph basically necessitated me making this butterfly graph and butterfly slice and scatter slices. This is what a butterfly slice looks like. It's who you call and who calls them. And it's also who you call and who they call. In my implementation, I stitch together any circumstantial direct relationships. So you'll notice down here in the bottom that puts is connected up to main through this edge over here. But puts is not in this graph because it's called by main. Main calls a whole bunch of other things. Puts is in this graph because it calls explode bomb. So I am doing just 2 levels here, and in the future, it'll be configurable, but for right now, it's fixed to 2 levels. And because I stitched those edges together, it doesn't look as much like a butterfly as it should. The idea here is you've got your one node in the middle with both wings as branches going out from there. So it looks like a butterfly. So let's take a look at that. Sweet. So you can go ahead, just create another slice. We're going to make a butterfly slice now. And when I'm in get input, we can see that it's called by main, which is called by start, and then all the functions it calls. And you get all that nice navigation again as well. I can double click into main, see all the functions that main calls, and then zoom into one of those. So that's pretty neat. Now if we take a look at this in a bigger binary, there we go. Click in. There we go. So this is going to be potentially an example of a isolated region of code that isn't called by other functions. We can see here at the top that the only function that calls the function we're looking at is something it calls, and then it calls into a bunch of other functions. I believe I have a slightly stronger example as well. I guess not. The risk of doing live demos. Oh, here it is. There we go. So you can see that this function here is calling into a bunch of other functions, and it's not called by anything else. So this function is a dispatch. But what it's calling, each of those functions are themselves dispatches. So I think that this is a really interesting part of the program that we'd probably want to analyze. And of course, it's followed by a whole bunch of external calls and syncs. So, moving on. We also have scatter slices. This is something I made up. If you guys know a better well-known terminology for this, I'd be happy to rename this. But this allows you to see cousins better. It's very similar to the butterfly graph, but instead of just going up and just going down, it recurses once at each step in the opposite direction. So here it goes up to main, and then it recurses down from main. It's great at finding cousins both through your parents and your children. I often say that these are functions that are in orbit of you or in proximity of you. So taking a look at that one. Oh, didn't mean to do that. We're going to do a scatter slice. And now we can see exactly that graph we saw before. If I go to main, it looks very much like the graph we were seeing before. This is a bit of a weird binary in that you kind of only have functions that call other functions that then don't have back edges, which in itself tells you something interesting about this program. But nothing we need to be concerned about for this talk. One problem you get from this, though, is that you have a lot of cousins, especially when going through your children and back up. So it would be nice to be able to have the ability to sort of pin portions of this graph or trim portions of this subgraph as well. All right. So you've found your points of interest. You've used the full call graph. You've used the butterfly graph. You've used the scatter graph. You found some functions that you'd like to be able to analyze. It's really important to be able to answer the question of can program flow transfer through one function and reach another? So let's take a look. We'll do this on BusyBox. This is a version of BusyBox that actually had a CV in it. There was calls to printf and system where there was a variable as the first argument, and that variable could be partially controlled by the user. Let's see. All right. So create that new slice. We're doing a source to sink graph. And if we go to one of those call locations right here, and I've just set up bookmarks to save us some time, but let's click in. Well, we can see, first of all, that call to system had a variable as the first argument, but where does that variable come from? That's what I'm trying to help you with here. So if we go to system, we can right click, Tonto, add this function as a sink. And here we get all the functions that eventually call into system. Now, this doesn't follow indirect data flow. If you have an out parameter that gets passed to a different function, and then that variable is passed by reference to another function, you're not going to get the data flow. This is strictly based on the call relationships of the program. Still very useful. If you have another function you're interested in, you can right click that, you can add it as a source, and then you'll get all flows between these two functions. And if you want to, you can go ahead and you can, like I said, system and printf were the vulnerable functions in here. So if I go to printf, I could also add that as a sink. And there might not be any relationships. There aren't in this particular case. I think if I removed this function, yeah, we get a much, much bigger graph. And printf and system are both somewhere in here as sources, likely towards the bottom, but not necessarily. So there's printf, and I'm not entirely sure where system is at the moment. So I also promised you better annotation tools, better note-taking tools. I think that graphs are super useful to be able to represent, well, kind of anything. We've been talking in other talks during the conference about the utility of graphs. So let's give you an example here. This was a CTF binary. And we don't even need to look at the code anymore. We can just use Tonto. It's the only thing we need now. So let's go ahead. We'll look at the full call graph for the program. And again, if I zoom out, it is likely too small to see. If we zoom in, we can start to recognize some patterns in here. We've got a big dispatch over here. And just to prove my point, it turns out to be main. But main calls into a bunch of these functions that have suspiciously similar structures. So let's take a look at one. Like right here. You'll notice that, so main calls this function, and then this function calls into a bunch of other functions that are isolated. They're just a tower. So let's take a look at that in linear. I can make a split pane over here, switch back to linear, and navigate back. You can see that this function just calls this function, which just calls this function. And eventually at the bottom, what we get is we're just returning the first argument. So reversing this program is terrible because you have to remember that these chains of functions eventually just return an argument. And there are more obnoxious patterns like this in this program. So I built this dynamic call graph, I'm calling it, to help address this problem. All right, so let's bring that over to the right. We'll put linear down on the left there. We'll go back to the function we were trying to analyze, and we'll go ahead and we will add that to our graph over here. Oop. So Tonto, include function and graph. From here, I can also include all the functions it calls. So you've got your callers, you've got your callees. The callees are the people I call. You can also, the all version just recursively goes through the tree and collects everything. But if we do just one level, we can see that this function that we were interested at the top there only calls these 4 other functions. And now if we try to find that sub B380 over here, we can see it in the middle. There we go. And if we navigate down to the last function it calls in that chain, we can now go ahead and add that function to the graph. And now we're analyzing a version of this graph, a simplified version of this graph, where we don't need to remember the intermediate functions. In fact, if we really want to, we can probably remove this node from the graph as well. And then we can see that the call from that function goes directly to the one we actually care about, the one that returns the argument eventually. All right. Oh, yeah, one more thing there. This is just sort of a neat little trick. You can drag and drop functions in too, and you can just start seeing where things are. So far, all we've exploited are call relationships. You can get a very long way just with call relationships. It's one of my favorite properties, underexploited properties of programs. But I promised you other types of slices as well. So this one's a little bit more for developers and researchers. I know we're probably all the same people here. You build your own tools that you then go use. But let's talk about dominance. It's very useful to be able to say for sure that one function has to execute before another. And dominance is the formalization of that. So one node dominates another if control flow has to exclusively pass through that node to reach the other. So in this case, A dominates B. In this graph, to get to D from A, you do not need to go through either B nor C. You can go through either B or C. So A dominates D, but B and C don't dominate anything because you don't have to go through one or the other exclusively to reach the other nodes in this graph. You can describe that nicely as a tree, and you can see here that A dominates D dominates E, but B and C don't dominate anything. We've also got dominator tree children, which is just going to be the direct children. So the children of A are B, C, and D. You got dominance frontiers and post dominators. Dominance frontiers are going to be sort of the merge points in your graph, the sync points, if you will. And post dominators, instead of showing you everything you need to execute to get from the entry of the function to you, it shows you everything that you need to execute to get from you to the exit of the function. So I built a handful of nifty visualizations for this. These are all going to be in the dev tools though, separated out. I do think they're very useful, but it's most useful when you're writing your own slice types. And all right. So we're going to go back to our slightly more simple binary over here, CFGs. And then use my fancy hotkeys to open up Tonto again. And let's take a look at, we have very specific instructions here, the Dominator tree first, because I think that's the most simple. Dominator tree, take a look at that. Now we have to open the left side on a graph as well. And we can see here that the Dominator tree for this function looks very similar to the function itself, but it breaks the back edge. We can use Dominator trees in our analyses to shortcut having to analyze loops in a lot of ways. All right. So if we go ahead and do our fancy trick, using Tonto with Tonto, I'll go ahead and open just the Dominator tree children under here for you, just to show you guys what that looks like. And you can see dynamically now as you're clicking around, it's showing you the Dominator tree children for the node you've selected. So that should be about what you expected. And then you've got your actual dominators. I will do that down here. Actually, check out your dominators. And this is just going to be basically walking up the tree we see on the top. And now I'll show you something really neat. Those dominance frontiers, which I didn't provide necessarily the best definition of, you'll notice that for these blocks over here, the dominance frontiers on the top right now, for each of these blocks in a loop, the while is in its dominance frontier. So as I said, these are sort of the merge points, the sync points in your graph. And one very nice property we can see on the screen right now is I have a node which has the while loop in its dominance frontier, but that same node, it dominates it. So from this node, you'll eventually go back to a node that you had to go through previously. That means your node's in a loop. Very easy one-line check to find if a node is in a loop. We can also now write a script to find XORs, and you can find decryption functions in a 5-line script. But just to finish up this demo, we've got our post dominators. Post dominators are neat. From that function, from that node, we have to go through the I+1 to the while loop, and then eventually we get to our return. Now, if you don't have a single return that you have to go to, none of them will actually appear in your post-dominator graph. Because again, it only shows the things you have to execute, not the things you might execute. So you've got a block and then you've got 2 returns after it. That block's going to be the last one you see. So it can be a little bit weird, be a little bit finicky to use, but worry not. I made a slice for the people. This is basic block slices. The direct application of program analysis can often lead to chafing, so I think that this just helps with that. So we'll close out of all of these and open, yes, our favorite demo here, our vulnerable version of BusyBox. Go ahead, open that slice. Basic block slices right at the top there. We'll find that potentially vulnerable call to system, open up graph view. And now this is a pretty big function, and I would like to not analyze all the blocks in this function, is the gist of it. So if we zoom back in and we find that call to system, we can right click it, and we can include this block in our slice. And now we get a new version of this function that's simplified. It's only the nodes that have to, it's only the nodes that will eventually flow into this block or will eventually get executed after exiting this block. So it's not quite the same as dominance. It's a bit more useful. All these blocks in particular may execute before we get to our block. But that's more useful for us as engineers because we don't necessarily care about just the things that will happen. We also want to see the things that may happen. But if you zoom in over here and you're like, actually, I don't care about anything above this loop, you can exclude that node and then you get an even more simple version. And you can see that we're highlighting the nodes that are excluded and included in red and green respectively. Now, a really neat demo I have in here is going to be, I recommend using a mouse with Binary Ninja. The trackpad is nice, but both a vertical and horizontal scroll wheel with graphs is useful. If we clear all the block states, I can pull out just a single case in this function. So I'll go ahead and add this block to our slice, and we get a somewhat minimal version of this program, but it includes the tower of blocks from the initialization. So I can go over here and click this node and exclude it. Oh. So we include this one, then we exclude this one. There we go. And now I believe, if I did everything right, you'll notice that there are a handful of nodes that are not executed between the two nodes that we care about. And that's because if you ever fall from this if statement into the false branch, you'll go to the return. You'll never actually reach that node we cared about. So this is helpful, again, just for helping us focus on what we want to analyze in the program. Cool. So, what else in Binary Ninja is a tree? The ILs are a tree. And there are multiple types of trees. So again, this one's for the devs. These slices are going to be in the dev tools. But yeah, also can't talk about Binary Ninja without talking about its awesome stack files. They're layered, they're tree-based, they're interactive. They've got a whole bunch of features. You can see over here, we go from assembly, down to, up to lifted IL, to medium level IL, to our high level IL. And nowadays we also have, high-level language representations. So you can go from high-level IL to pseudo-C or pseudo-Rust or pseudo-Python or pseudo-Go, whatever you want. And that's pluggable as well. We do different analyses on the different levels of IL. So when you're implementing your slice types, you're going to want to do your slices on different levels of the IL as well. And they're extremely interoperable. And I said they're also extremely scriptable. This is how you get every instruction in the program. And instruction of decompilation of our high-level IL. So you go through all the functions, go through each basic block in the function. You can do your dominance properties on those blocks if you want to, and then you get each instruction and pull out the operation and the text for it. But I said that the instructions are a tree, and there are two types of trees. Each instruction itself contains other instructions. So an assignment is going to have a left-hand side and a right-hand side. That right-hand side could be a function call, and that function call can have parameters, and those parameters could themselves be function calls or addition or any number of things. So when you're working on your slice types and when you're working on your analyses, it's nice to be able to break those, to see what those are. All right. So let's take a look at it. Doesn't matter what binary we look at now. Let's just open up Tonto and we'll look at the instruction graph. Go back to that call to system we care about. And if I click on that, you'll see that call to system is inside of a high-level IL variable initialization, where the left-hand side is a variable, and then the right-hand side is a call. But the parameter to that call is an addition, and that addition has a left-hand side and a right-hand side. So when you're writing your scripts and you're trying to process these instructions, we've got a couple hundred IL instructions. And some of them are very similar. Like we've got tail calls, we've got local calls, got other types of calls. So it'd be nice to be able to say, I just want all the calls. I know they all have destination. I know they all have parameters. And that's what the hierarchy is for. So when you look at the hierarchy, the instruction objects in our API have inheritance. So this high-level IL variable initialization inherits from setVar, which inherits from the base instruction type. So now you can, instead of doing finding all the high-level IL variable initializations, you can find just all the setVars. Now what's really cool about this is this allows you to write both architecture agnostic code because you're writing over the ILs, but it also allows you to write IL agnostic code because this inheritance structure is in all of our ILs. So now you can write analyses that work on high-level IL, but then you find out you're shooting yourself in the foot because there's too many simplifications, there's too much code folding, whatever it is. So then you can drop down to the medium level IL and still have your analysis work when you're using the common IL classes, is what we call those. Now I click into system, we can see that, well, actually I clicked on the call destination, so that's a constant. But if I click the parenthesis there, you can see that this particular call is a local call, but it is also just a call, which is part of the class of control flow instructions in the program. And we can just keep clicking around and finding all the different cool relationships here. But let's move on. So, yes, the IL is a tree, and that means recursion. So if you're writing things, you're going to get used to this traverse function. This is one of the most powerful APIs in Binary Ninja. It is also by far one of the most complicated APIs in Binary Ninja. For those of you just coming in, feel free to come get a seat. There's plenty. I don't mind the shuffling. All right. And then for the common IL classes, this is sort of what that looks like. So you can get the direct operation and match on the enum, or you can instead ask if this instruction is some type of call, and you can get more specific using the other common IL classes as well. All right. So variable slices. No more developer slices from here on out, just cool things to solve cool problems. This is also one of the original 2 slice types that I made in Tonto 1.0. It had the basic block slices and now also the variable slices. So let's take a look at our favorite example again, BusyBox, and we're going to do that variable. So create a new slice type, find the variable slice option, hit OK, and now we want to find where this argument is coming from. Can it be affected by a user? So let's right click it, Tonto, include this variable in the slice, and now you get a version of this function from the perspective of this variable. Any instructions that have to be executed to get to the particular use of the variable you care about are shown, but if they don't actually affect the variable, they're grayed out. So we go to the top here, we see that R11_1 is being assigned to this R6_1. Where does that come from? You can start going through, and you can now add that variable to the slice as well. And it'll show you all the places that that variable is coming from. And you can keep going ahead and doing this, but we know how to script over the ILs. We know how to pull out different classes of instructions. We know how to work among functions as well, so we can do better. And that brings us to the intra-procedural data flow graphs. These last 2 slices I'm going to show you guys are not being released. I still need to do a bit of work on them. It's hard. It's a hard problem to solve in the general case. But let's take a look at it. So intra-procedural within the function is going to give us intra-procedural, go here, go to that variable we care about, and then just select the variable. And now this is using SSA, so sorry for the extra complication there, but SSA is really useful for data flow analysis. We can see that the instruction we care about is on the bottom there, and it comes from assignment of this other variable. And now we can see that variable is the merger of two other variables, one of which is recursively defined, and the other has three other sources. And then we can go up from there, and eventually we find that the source for the parameter to system is coming from this function call, that function call, and argument 1. So, as I said, we can do better. We can do things interprocedurally. On this particular binary, it'll be a bit too complicated. So let's go back to our simple example. And on the left there, you can see this check answer function, which gets RAX1 from get input. And RAX1 turns into arg1 as compared to this. So what we'd love to see is click arg1 and see that it's coming from get input. And if everything goes right, that's exactly what will happen. And there we go. So we can see the use of arg1 in the check answer function at the bottom of our graph. And then we can see that it comes from get input. All right. So we've solved a lot of problems, but there's still some to be solved. In particular, one of the first things people usually ask me is, can I include and exclude edges instead of just nodes? Currently, no. I need to add that. That'll enable certain slices that are currently impossible. I also said that we need more configuration options in Tonto. So have more settings, be able to configure your slice depth. It'd also be nice that when you're analyzing things, you don't lose your slices when you close your binary view. I already have the framework for this, but it's just not saving them yet. And those indirect relationships in call graphs, we really would like to be able to trace the data flow throughout parameters. I don't have that yet. As I said, it's a hard problem. And there's more we can automate. Mandiant Simplify Graph shows us that we can basically automatically find regions of code that can be collapsed into, more simple things. And Ghidra has a couple tricks as well that we could implement. And hopefully you guys can create your own simplifications, do your own research, make better visualizations. For the interprocedural data flow graph, I actually think that it'd be really nice to show flow graphs within flow graphs. Just haven't gotten there yet. So, and yeah, I have a dozen other slice ideas as well. Feel free to pick my brain after the talk. So what have we solved? We've reduced the discovery time for points of interest in a program. We can look at the call graph of a program, immediately recognize patterns, immediately recognize places we want to zoom in on and start analyzing. Read less code or none. When we looked at the Bomb Lab example, we didn't have to read a single line of code. We were just looking at the names of the functions and figuring out what the program does. We can identify those regions of a graph that we don't need to analyze. We've automated source to sink based on call relationships. We've explored navigation and exploration with the butterfly graphs and scatter graphs. We do have we have actually lots of control flow slicing and some data flow slicing. I tricked you guys into learning dominance and how to work with IRILs, so now you can do whatever you want. So thank you for listening to my talk, A Slice of Modern Program Analysis.
So we have more or less 1 minute, 2 minutes for questions. Are there any questions in the room? Raise your hand.
Yeah, thank you for the talk. So a question I had was, in one of the examples you was looking at the call flow to system.
Yep.
And I was wondering if that works recursively within shared objects. So, for example, if you had a parameter coming from argv, and then it goes through multiple shared objects and then eventually hits system, would you be able to have that in the call flow?
So I told you that interprocedural is hard. Now you want me to do interfunction or interbinary? Binary Ninja does have some like project support to let you analyze stuff like that. And I think the least baked slice I have in this talk is the dynamic call graph, because that one in particular, I think that it would be really useful for you to be able to add those external nodes and be able to analyze those flows. So I'd love it, but not currently.
Yeah, thanks.
We're entering timeout. Maybe a short question. There was a hand raised a few seconds ago. Not anymore. Okay, let's wrap it up. Thank you, Kyle.
All right, thank you.